Howdy, and welcome to Inversions. Air temperature inversions provide near-perfect conditions for tiny aerosol-sized droplets to drift away from their targets. Understanding inversions is essential to following state and federal regulations that prohibit pesticide application during inversions. Observing pesticide manufacturers' warnings about inversion conditions on product labels and preventing unintended pesticide contact with non-target dissipation requires a basic understanding of energy transfer at the Earth's surface and in lower layers of the atmosphere. The microclimate is defined as the climate near the ground. For our purposes, it consists of the lowest 20 to 30 feet of the atmosphere and the soil surface or anything covering it, and the top foot or two of soil. The microclimate is best characterized as a region with rapid changes in air temperature, wind speed, humidity, dew point temperature occurring over short distances and in short periods of time. It is also a region of air and surface temperature extremes. Surface characteristics usually determine weather conditions in the microclimate, especially when wind speed is low. Understanding air temperature inversions require a basic understanding of numerous energy transfers that cause the Earth's surface temperature to increase or decrease and microclimate air and soil temperature to change. Surface temperature always refers specifically to the temperature of the Earth's soil surface or the surface temperature of anything covering the soil surface that is exposed to the atmosphere. It is not air temperature. Air temperatures vary greatly near the Earth's surface depending on weather conditions and surface characteristics. For example, around sunrise on a clear, nearly calm morning, air temperature measured 5 feet above the surface may be 4 to 10 degrees Fahrenheit greater than the air temperature measured near the surface. Conversely, in early afternoon on a nearly calm, clear day, the air temperature at 5 feet could be 4 to 15 degrees Fahrenheit less than the air temperature near the soil surface. Actual air temperature depends on surface conditions. Standard air temperature measurement conditions were established in the late 1800s so that air temperature measurements from different locations would be comparable. As a result, official thermometers were located at a standard height of 5 feet above a turf-covered surface. They were placed inside a white louvered box with a double roof to shield them from direct and indirect heating by the sun and direct radiation cooling to the clear night sky. Surface and air temperature variation daytime. Clear skies with little to no wind absorb solar radiation, begins to heat the Earth's surface shortly after sunrise. As the surface temperature increases, energy from the warmer surface slowly is conducted into the cooler soil. Conduction is the process by which heat energy is transferred from warmer to cooler areas by molecular contact. The interior of the solids can be heated only by conduction. Simultaneously, energy is conducted from the Earth's surface to the adjacent cooler air molecules. As the sun continues rising, more and more solar energy is absorbed and the surface temperature continues to increase. Also, simultaneously, more energy is conducted into the soil and the overlaying air. As the air temperature near the surface increases, the heated air expands, making it less dense than the air above it. This lighter air begins rising while the cooler, denser air above it begins sinking. When the cooler air reaches the surface, it is warmed by the surface and rises simultaneously, allowing cooler air to descend. Thus, tiny circulation cells are formed that slowly warm a thin layer of air near the surface. As the sun continues rising, solar rays become more perpendicular to the surface and surface heating intensifies. This causes the tiny circulation cells to grow larger vertically and horizontally. As surface heating continues, rising columns of warm air continually transfer more and more heat energy from the surface to greater and greater heights, and the descending air around each column transfers cooler air to the surface to be warmed again. Energy transfer by the spontaneous movement of air or liquid is called convection. Convection cells continuously grow larger as surface heating continues and eventually can reach heights of 100, 1,000, and 5,000 feet or more by early afternoon on a clear day. The appearance of late morning or afternoon cumulus clouds that often form at the top of rising warm air columns are proof that convection is occurring. All clouds absorb, reflect, and/or transmit incident solar radiation. Water droplet clouds form at low altitudes, have sharp, distinct edges, and usually appear bright white because they reflect 30 to 90% of the incident solar radiation back to space. In contrast, ice crystal clouds generally are found above 20,000 feet, have fuzzy edges, appear stringy or fibrous, and reflect less solar radiation. The greater the cloud cover, the more solar radiation is reflected back to space or absorbed by the clouds. Clouds reduce the amount of solar radiation absorbed by the Earth's surface, so it warms more slowly than on clear days. On overcast days, only the solar radiation that's transmitted through the clouds reaches the Earth's surface. Clouds also emit and absorb long-wave radiation that causes major effects on nighttime surface cooling. Mid-afternoon through nighttime, clear afternoon and night throughout a clear day, the Earth's surface absorbs enough solar radiation to heat 5 to 10 inches of soil and several thousand feet of air. Simultaneously, the Earth's surface, or whatever covers it, has been emitting long-wave terrestrial radiation into the atmosphere. The greater the surface temperature, the greater the terrestrial radiation emitted. When the terrestrial radiation passes through the clear atmosphere, water vapor and carbon dioxide molecules absorb some of the radiation. The remainder is lost to space. Simultaneously, the water vapor and carbon dioxide molecules emit long-wave radiation in all directions. Some of this long-wave or atmospheric radiation is directed towards the Earth's surface, where nearly all of it is. Without this added energy from the greenhouse or atmospheric effect, the Earth's average temperature would be about 59 degrees Fahrenheit colder. The maximum surface temperature occurs when the solar radiation plus the atmospheric radiation energy absorbed by the Earth's surface equals the surface's terrestrial radiation lost. Depending on the amount of time the surface takes to warm up, the maximum surface temperature usually occurs 2 to 4 hours after solar noon, and the maximum air temperature is reached shortly after that. Given clear skies, the Earth's surface temperature begins decreasing in mid to late afternoon, when the surface is emitting more terrestrial radiation energy than it is receiving from solar and atmospheric radiation. Wind speed is zero at the surface and increases exponentially with increasing height. Any surface unevenness or obstruction causes air to flow over or around it, resulting in horizontal or vertical eddies of various sizes. The result is chaotic, random, swirling motion called turbulent flow, in which wind speed and direction change rapidly. During an inversion, these eddies cause air from greater heights where wind speeds and temperatures are greater to mix with or replace slower moving, colder air near the surface. Inversions are generally stable enough to resist this mixing action when wind speeds are less than 4 to 5 miles per hour. As wind speed increases, inversions steadily are weakened and only weak ones will form. However, even in the windiest cases, surface temperature still will be less than air temperature because the surface is cooling continually on a clear night.